Hello, are we ready to start? So, as always, I ask you to turn on your cameras and microphones and to take part in all of our discussions. You have such an opportunity, I mean about camera, but participating in our discussions is encouraged even without camera. Okay, let's start with solving the regular set of problems we have for today. I hope everyone has the paper with the problems for seminar 4, and I've already shared you a board. And I'll share you my screen with this board. But if it's more convenient for you to use it in your browser, feel free to do it. Okay, so let's start with the first problem. At the previous lecture, you studied multiplicative groups of some cyclic groups. First of all, you knew those groups as additive groups, and then you studied their multiplicative groups. So let's start with the third problem. It looks like the most, the easiest one of all these four first problems. Let's take cyclic group of order 5, and let's consider all the elements which have inverse elements as a multiplicative group. So I write down a star here, and let's find all the generators of this group, I mean multiplicative group. So let's remember first of all what is the order of this group and some of its properties. First of all, we know that since 5 is a prime number, the number of elements equals the order 5 minus 1, which is 4. So all the elements except 0 have inverse elements. Do you remember such a fact? If you don't remember, ask me a question and tell me what is, what shall I repeat and re-explain, maybe. So no questions now, okay? Okay, then we know that all the elements are invertible, and this group of all the of all the elements which have inverse element is cyclic. This is also known from the lecture. This is a cyclic group. So we have to find the elements which generate the cyclic group of order 4 in this kind of notation. Let's find. For example, take 2 and consider all the powers of 2 modulo 5. The first is 2, the second is 4, the third is 8, which is 3 modulo 5, and the fourth is 6, which is 1 modulo 5. Do you agree with this speculation?
Yes.
Yep.
So my question is 2 a generator of our group? Oleg, tell us, please. Is 2 a generator?
2, it's 4 to 2 in part 2 is 2 is 4. 4 multiplied by 2 is 8 modulo 5 is 3. Yes, it is.
Yes, it is, because it generates all the elements of our group. 1, 2, 3, and 4. Okay, so our group, that 5 start, is generated by 2. Are there any other generators?
Can I ask a question?
Mm-hmm.
You have started with saying that let us consider all the elements from this cyclic group which have inverses. Like,
Yeah,
why do
yeah.
so,
I
like,
know. Why?
I mean the elements which do not have inverse elements, like, do they not belong to this group? Like, could
Yes,
this be
by definition, such a group Zn start consists of all the elements x from Zn such that there exists x to the minus first power in multiplicative notation. So for every element, there exists the inverse element, the inverse additive element, which is minus 6, merely minus 6. For example, for 2, this inverse element is minus 2, which is 3 modulo 5. Yeah, it's not a problem. And for 0, this is also 0, because 0 plus 0 equals 0 in additive case. Yeah, so we consider sometimes Z5 as an additive group. And then we would like to consider all the reminders modulo 5, but not additively, but multiplicatively. We know that we can multiply reminders and all their good conditions hold. So let's, for example, take 2 numbers and we know their reminders modulo 5. So the product of these numbers have the remainder, which is the product of 2 reminders. Okay?
Oh, by the way, I have also figured out, I remember while solving some of our homeworks, that, for example, the cardinality, I mean, okay, the order of an element is equal to the order of its inverse. So we can say if we find the inverse of 2, we can say that it's also a generator of this.
Right, yeah, that's right. So we consider now all the reminders, but the operation on the reminders is multiplication. And we want our reminders to be a group. So what can prevent our reminders to form a group? First of all, some of the reminders might not have inverse reminders in this set of reminders modulo 5. For example, 0. How can we multiply 0 by anything to receive 1? It's impossible, yeah? So 0 has not multiplicative inverse element, you see? So this group, Zn start, doesn't contain 0, for example, yeah?
Oh, sorry, do you mean to scroll down, because
Okay,
it's impossible
yeah.
to...
I see.
Thank you.
Okay. So, for example, this group doesn't contain 0. And it's always the case, because we cannot multiply 0 by something modular. For every modulus, yeah, we can't multiply 0 by something and get 1. Okay, we always get 0 reminder. So we throw out 0, and for some orders, I mean here 5, for some n's here, it turns out that all the other reminders have inverse elements. In the lecture, Dima explained you that if n is a prime number, and here we have prime number 5, the set of all the reminders which have multiplicative inverse numbers, multiplicative inverse reminders, if you want, this it's the set of all numbers except 0. So this group, multiplicative, so this multiplicative group it's the same that we take Z5 minus 0, and the operation is multiplication. Okay, this is the fact from the lecture, right? And this is a group because it's associative.
Shouldn't it be Z star because the operation is multiplication, and but Z?
Yeah. Here, this is Z5 start.
Mm-hmm.
So this is a set of elements. This is this notation of not a group but a set of elements.
So I got it. I got it.
So
I have a question about notation. Sorry for interrupting. Can I ask it now?
Yeah, okay.
Because sometimes we, by like putting some set with these asterisks, we mean different things. Because, for example, it will be even number here instead of 5. Then we consider this group as this set is all coprime numbers with our.
Right. Of course, we consider all the numbers which have inverse. So sometimes not only 0, but some other reminders don't have inverse reminders. And so we throw out all of them. Okay?
Mm-hmm. But the star doesn't mean some exact operation. It means that from the set we do something that can be a group with this operation.
Yeah.
Okay.
Correct. The set means two things. The set means two things, that this is a group. So we this is a multiplicative group. So this means that the operation is multiplication, and all the elements we take to this group are the following elements. Only those who have inverse reminders. So
okay, got it.
It's always multiplicative, and only invertible reminders are in this group.
Thank you.
Okay, so let's go on. In our case, we know that the group of reminders consists of all the non-zero reminders. And this is a group of 4 elements, and we also know that it should be a cyclic group, and we found one of its generators. The question is, are there any other generators? Why yes or why not?
Well, as I have
yes, there is.
Which one?
And this is like other elements of the set.
All of the elements. All of the other elements, or some special elements.
For example, one. Oh no, one is neutral.
By one, it's also one. Okay. Mm-hmm.
Yeah. Yes. Sorry. I mean, wait.
In our case, we can check directly. We can take 2, and we can take 4 and 3. 4 times 4 equals 16, which is 1. So the order equals 2. It's not a generator. And here we can take 3, and 3 to the second power is 9, which is 4. Yeah, and 4 by 3 is, okay, sorry. 4 by 3 is 12, which is 2 modulo 4, and 2 times 3, which is 6, and this is 1 modulo 5. Yeah, okay. So 3 is a generator of our group. Okay, so how can we find all the generators? In this case, the order of the group is very small, and we can check all of the elements. But remember, how do we always represent cyclic group of order 4? Which is a natural way to represent a cyclic group of order 4. This is the following one. Z4 with addition. Okay?
Okay.
So what are the generators in Z4
Uh,
in additive notation?
um,
I already told you that this
it's
is
it's an additive. Sorry, okay, it's an additive. Then yes, 1.
1 and 3.
Mm.
And the generators, because of their coprime with 4. Yeah.
So only so like only the elements which are coprime with the group order is
Surely. Set of the generators for our cyclic group Zn, in our case Z4, is a set of all coprime numbers with the order. So in our case here we have only 2 generators. So Z5 start should have also 2 generators. Okay.
But this works only for additive notation, because I remember
This
that.
works for additive notation, but let's note that this group is isomorphic to this one. Why they are isomorphic? Because they are cyclic groups of order 4, and we can take some arbitrary generator here, let it be 1, and map it into a generator here. We know that 2 is a generator. We've checked it already, okay? So we should check, we should find only 1 generator in this group, which is not as easy as here, yeah, to check this. But we can construct a homomorphism which maps this generator 1 to this generator, and then every element k goes to 2 to the k's power in multiplicative notation, and this is an isomorphism, you see? Because it's injective, it's surjective, and it's a homomorphism. It's a homomorphism because we built it in this way, because phi of 1 by A goes to, this is a power in additive notation, you see? Here, let me move it. Okay, so that goes to 2 to the k's power. In more detail. Now, what is k? It's 1 plus 1 plus 1 k times. Goes to 2 by 2 by 2 by 2 k times. You see? So this is a homomorphism. It's injective and it's surjective, because for every element here in our group Z5 start, we can, every element can be represented as 2 to some k's power, and what element in Z4 goes to this one? It's k. Okay? Is it clear, this explanation?
Well, yes.
Yes, so these groups are isomorphic, and algebra studies groups up to isomorphism. So strictly speaking, it's the same group, okay? So
I have a question.
Ask, please.
In this case, it is very simple to find isomorphism as well as check every like cyclic, not cyclic subgroups, but as well as generators. But for example, if we consider a very big group,
for example, Z17, as in the first problem.
Yes, it will be like the boss tasks will be pretty untrivial to find a subgroup, and to find isomorphism.
Honestly, the second way to find one generator and to find the one generator and the problem of finding all the generators using brute force, they are not equivalent. To find one generator and to construct an isomorphism is easier, because we need to find only one generator and isomorphism is the same as in the previous case. Let's consider the first problem where we have Z17 start. Okay? The first problem. And we need to find all the elements of order 16 in this group Z17 start. What do we need to find? Strictly speaking, we need to find all the generators, because only the generators have order 16, and if an element has order 16, it generates all this group, because the order of this group equals to 16. Agree?
Yes.
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 It's also 16 because 17 is a prime number, so this group consists of all non-zero reminders. All of them have inverse reminders, and so on and so forth. So, okay, we should find, first of all, we should find only one generator. Let's try to find one generator here. How do we find it? Okay, let me...
We know from Lagrange theorem, we know the connection between the order of element and the cyclic group which it creates.
Mm-hmm. And how can we apply it now?
Somehow.
Okay, here for Z17, for Z16, for a cyclic group with addition, Z16, we know all the generators. It's very easy to know, to list all of them. It's 1, 3, 5, and all their coprime with 16. But we don't know now how do they look in Z17 start, because the operation is multiplication, and it's a bit more complicated. But let me give you one of the answers. I know that 2 is not a generator, but 3 is a generator. You can easily, honestly not easily, but you can check it. Here, 3 generates our group. Honestly, it's not very difficult to find 3 to the 16th power modulo 17. 3 to the 16th power is a big enough number, but we don't need this one. We have to find 3 to the 8th power squared and 3 to the 4th power squared, etc. You also remember this from your lecture, yeah? And on every step, we should reduce the result modulo 17. So their powers won't be very big, okay? All of them will be less than or equal to 17. So 17 is 0 modulo 17.
But we also know this from the course of number theory in discrete math.
Okay, great.
And we can consider, for example, 3 in second power modulo 17 is 9 modulo 17. So we reduce it until 9 in 8th power, and still it's a big number. So we can do it again, 27.
97 modulo 17 is 10, yeah?
Yeah, it's 10. And then we will have 10 in 4th power modulo 17.
Not 10 in 4th power, but 10 multiplied by 3.
Oh,
These all are powers of 3. So we multiply 10 by 3, this is 30, which is 3 modulo 17. So this 3 to the 4th power is merely 3, okay? So to the second power and to the second power. This equals 1, and 16 is the smallest power in which we have 1. So 3 generates this group. Okay, we've almost checked it. So knowing one of the generators, how do we find all the set of the generators? Using their isomorphism. Let's construct such an isomorphism from our group generated by 3 to our cyclic additive group Z16, which is generated additively by 1. And we map this generator to this one. So our homomorphism of 3 equals 1. And then it means that phi to the minus first power of 1 equals 3, because it's an isomorphism. We can map from the left side to right side and from the right to the left. Okay? So we know all the generators of Z16. What are they? They are 1, 3, 5, 7, 9, 11, 13, and 15, and that's all. Okay? Is it clear?
Sorry. No, sorry, I don't understand here. Can you repeat, please?
These numbers are generators of Z16 as an additive group, because the generators are those elements, those and only those elements which are coprime with 16. Is it clear, this statement?
Yes, thank you. Yes.
Okay, so you have a question? No? So now we should apply phi to the minus first power to all of these elements. Let it be denoted by psi. Here we have phi, and psi is a phi to the minus first power. It's inverse isomorphism. So how does it map our elements? It takes psi, takes some element, first the 1, and moves it into 3. And for every other element, k, it's psi of 1 plus 1 k times, which goes to 3 by 3 by 3 k times, because it's an isomorphism. And it's equal to 3 to the k's power. So for every element in our additive group k, psi of k is 3 to the k's power. And now we have to take all these elements, 3, 5, 7, all these generators of Z16, and find 3 to the first, third, fifth, seventh, etc. powers modulo 17. All of them modulo 17. And all these powers will be the generators of our multiplicative group. Is this explanation clear for you?
So like we just take all the elements which first are prime with the number n, which we have, and then we also create a mapping from the additive group, and just then get also which elements are there mapped to the generators, and then they are also prime, or what?
And they are also the generators of our cyclic group. Because
I just
have-
did. Well, I just didn't quite get why it's 1, 3, and 5, and 7. Like they are just prime numbers. What?
it turns out that not all of them are prime numbers. Here in this column, 1, 3, 5, 7, 9, 11, 13, 15. The question is about them, yeah?
Mm-hmm.
They are not prime, strictly speaking. They are co-prime with 16.
Oh.
And they are generators of our cyclic additive group of order 16. But if we have an isomorphism from our cyclic group of order 16 to some other cyclic group of order 16, which is Z17 start, they are both isomorphic groups, okay? And the operations are different in those groups, and the elements act differently in those groups, but there is a mapping, a bijection between the elements, between the sets of elements.
3 psi of k is 3 in power of k, but like, how did we get this? This 5, 1 is 3. I mean 5, 1.
This k is an element of additive group, okay? So psi maps elements of this group Z16 to this one, and it maps the generator 1 to the generator 3. Okay.
So
and now I use the definition of homomorphism.
So like the psi is a bijection between these two sets. Yes.
So the question is, why is it a bijection?
No. I'm just asking whether it's a bijection. Well, it's clearly should be, because we define it to be equal to phi in power of -1. So okay. I got it now. Thank you.
I didn't get the last statement.
No. I just didn't get what we did, and then I got. So okay.
Okay, nice. So can we go on?
Okay.
Is it clear now?
Well, it is. Okay.
Is it clear that we've solved our problem? The only thing we need to find directly 3 to all of these powers and list the set of all these numbers. And we've solved the problem. Okay, so let's try and solve some else problem.
Wait, I don't get why all this. Sorry, I don't get why all these elements are order 16.
Which ones? This column or these 3 to some powers?
3 to some powers.
Okay. What are the elements? They are images of all the elements of power 16 in the group. So we have 2 isomorphic groups, yeah? And we know that in one of these isomorphic groups, this column of elements is a set of elements of order 16, because they are the generators. And only these elements have order 16. And in the isomorphic group, which we consider Z17 start, the images of all these elements are the following elements. So the properties of these images are the same as the properties of these elements. So we only need to find the images of these elements, and automatically the order of the images will be 16. So this is the explanation. The short answer is because 2 groups are isomorphic. And in isomorphic groups, corresponding elements have the same properties. So is it clear now, Michael?
Sorry, I had a broken internet connection and
Okay.
I've skipped the last minute of your speech.
Okay, let me repeat. The short answer to your question is the following. We consider two isomorphic groups and the properties of corresponding elements in isomorphic groups are the same. This is the short answer. The long answer is the following. We built an isomorphism from Z16 to Z17 start such that these elements goes to these powers of 3. And we know in Z16 that the power of the order of all these elements equals 16. So the images of these elements also have order 16.
Okay, got it.
Nice. Any other questions? No questions? Okay, so let's discuss.
Sorry, I have one more question. Do you mean to share the Miro board? The link for Miro board. So
Okay, let me do this again. First of all, in the beginning, I've already sent the link, but new people can see the link. Okay.
Thank you.
Not a problem. So let's discuss some points concerning the fourth problem, because here we don't have a prime order. 125 is not a prime number, and we can say that the order of our group of invertible numbers equals 142 and 24. So what's the order of the group in the problem number 4? How can we find it? What do we remember from the lecture?
Using the Taushin function.
So, what is the order of our group? It is 5 of 125, yeah? The number of co-prime with 125, yeah? So how can we find this number? Do you know some facts helping us to do it?
It is 5 numbers.
We can find all the numbers, but there are lots of them. Co-prime with 125.
We used some formula in our discrete mass course for Taushin function, and is it okay if I Google it?
Oh, wait. We have to find a Taushin function for which element?
125. Because this is the order of our group.
We can. It's very simple. We just can decompose it in a primally factorize, and then find the Taushin function for each prime and its factorization.
Yes.
So, and then,
so this is 5 to the 3rd power. So we should, for the powers of prime, which is the formula?
Then it's 4 in power of 3.
For the primes, it is n-1.
For the primes, it's the prime minus 1, but for the powers of primes, is it 5 to the 5 cubed minus 5 squared?
No. It's. Oh, maybe it's like this. I just know that it's like 5 minus 1 in power of 3, because like we can just decompose it into 3 distinct parts.
Could you write it down, please? Because I.
Where? On the desk?
Maybe on the desk, on the screen, in the chat.
I hope I'm getting it right. Let me understand how to do this first. Okay. Okay. Do you see anything? No. I mean, I'm writing on like in Zoom. No. Okay.
Not yet.
Drawing. Oh, wait. Here.
Here I see now.
Okay.
You're writing it in Zoom.
Equal to phi of 5 cubed is equal to 5 minus 1 cube. As far as I know, well, I think that it should be true, at least.
Okay, let's check for some simple cases. For
I
example,
remember
something like
4 cubed, or it's 5 minus 5 squared. Oh, wait. You were right. It's 5 cubed minus 5 squared.
Is
Yeah,
5 cubed
I was
minus
wrong.
5 squared. Yeah.
Yeah, so
And for coprime numbers, if n and m are coprime numbers, 5 of the product equals what? Tell me, please.
5 distinctly of their product, no?
5 of n times 5 of m. Yeah, right. The product of all the functions. So, great. So, using this fact, we can find the number of elements in our group, which is 100. So now we know that all the generators of our group have order 100, and we'll try to find all the generators. How do we find all the generators in our case? First of all, let's find one generator. So we are not going to solve the whole problem, but only discuss some key points. So let's find one generator. For example, take 2 and 3 and 4 and take some of them and try. No, but don't take those ones which are divisible by 5. Yeah, they are not useful. But take those which are not divisible by 5 and try some of them, and eventually you find one generator. Spoiler, one of these generators is 2. So this group can be generated by 2. And you can easily find the 100th power of 2 using the first, the previous explanation, yeah, from the previous problem. So this group is generated by 2. And then, knowing that this group is cyclic, and knowing that this group is isomorphic to a cyclic group of order 100, you easily find all the generators of a cyclic group of order 100 in additive notation and map them into the powers of 2. And you can list all the generators of our group. Okay? Is this plan is clear for you?
Yes, it's clear.
Okay, nice. So now we won't solve the whole problem. Let's solve something concerned to the next topic of your lecture. Let's try and encrypt some messages. First of all, let it be the problem number 5. Okay, we already know, we've already worked with a group which we have in this problem, yeah? And let's solve this problem. First of all, we have a group which is Z5 start. The element G previously chosen equals 2, and we use a table which maps elements from our 4-element multiplicative group to some binary expressions. Yeah. So we know that the public key is 3, And what is the public key? Do you remember? The public key of the other person.
Like it's the key which everyone sees. So
Yes.
I forgot
And
just how to define it. Like it's something in the power of something. Yeah, it's like our private key in some power. But like it's because it's a we have to solve the problem of discrete integral. We cannot clearly understand what is the private key, even seeing the public key.
okay, so we know the base. We've previously chose the base. Yeah, the base is G, and the power is B, but we don't know the power. This is a private thing. Yeah, only the other person knows B, but we don't know B. We know A, and we know G. All of us know G. Okay, so we chose a private key to be 2. So we can compute some things. A, we can compute our public key R, which is G to the 8th power, which is 2 to the 2nd power, because we've chosen.
What is, sorry for interrupting, what is A?
A is a power we've chosen to be a private thing for us. So all of us act as the first person, and something in the task acts as a second person. Okay, so we've already checked G, and it's our common number, and we, the first person, checked A to be 2. So our public key 2 to the 2nd power, which is 4, in our multiplicative group.
Yes.
And the person chose some B, which is private, and says us that G to the B to the bth power equals 3. Okay, so we've already computed the first point. Yeah, we computed our public key in our group. Then let's compute the secret key, K, which is G to the power AB. How can we compute this key, knowing only A and G to the bth power? Tell me, please.
And what is B actually? I don't get it.
B actually is the number we don't know. Look here. B is a power that was chosen by the second person, and we don't know this one. This is a private thing, and we know only S, which is G, commonly known G, to the bth power. This is B. Is it clear now?
Almost. Okay, I got it. I think I got it. We know that 3 is G in bth power.
Yes, but
so we know G, so it's pretty simple. We have to find the 3, like we have to find logarithm, but in this case, as it is cyclic group, it is not logarithm.
It's discrete logarithm.
Okay, I don't know, what is it?
It's called discrete logarithm. It's naturally to call it logarithm. So it's pretty simple when we have Z5. It's pretty simple, but it's not as simple in some other very huge groups. Okay, remember the order 125. We needed some facts from the number theory even to find the order of this group. I'm not speaking about their powers and the logarithms in this group. So our only way we can apply always is a brute force. but it's not very simple for a huge group, okay? So now it's a toy problem. It's not very complicated for 5 numbers for Z5, yeah?
It have to be 3.
Maybe. But how can we find G to the power AB without actually finding B? Let's imagine that it's complicated even now to find B.
Mm-hmm.
And how can we find G to the power AB? We know A and we know G to the power B. Let's swap A and B and find this power. This is the same because our operation is commutative. Multiplication of reminders is commutative. Yes? And we know that this is G to the power B, which is known. It equals S to the power A. So this is S to the power A, which is 3 to the power 2. 3 squared equals 9. It's 4 modulo 5. Right? Guys, do you have...
Why? Because we know G in power of B is our secret key. Secret key. Okay, got it.
Okay, nice. What's next? We computed the secret key. We know the message 2321, and we want to recover the original message. Let's remember. Let me write it down. ABC 2321. So let's remember what the message means. How the second person constructed the message. Do you remember how to construct a message?
No.
No. Let me remind you some of the points. So we know that let us denote, it's already denoted by key, this public key, yeah? And there is a message, H. The second person has a message, H, and he or she wants to send it privately. So having this number H, the second person takes M, which is a product of H and the private and the public key K, right? And then this message M by message, yeah, it's sent to the first person, to us, and we receive M. How can we find H knowing M and K? H is merely M, K to the minus first power, right? And in the cyclic group of order n, minus first power is the same that n minus first power, right? This is M, K to the n minus first power, where n is the order of our group. Now n equals 4. Because our cyclic multiplicative group consists of 4 elements. So we now have message 2. What is H? H is 2 multiplied by our K. K is 4, yeah? to the minus first power. What is the minus first or third power of k? Which number should I take to be the inverse for 4? Tell me, please.
1.
By 1. I multiply 1 by 4, and it is also
Sorry, it is 2.
4 times 2 equals 8, which is 3 modulo 5.
4 times 8, which is 3 modulo 5.
Excuse me, what do we have to find at the moment? Because I lost the point.
We have to find this guy, 4 to the minus first power. It is also 4 to the third power. Because there are 4 elements in our cyclic multiplicative group. So
is
we multiply 2 by 4 by 2, it's 3 in our group.
So 3, yeah. So it should be 3.
Let's check. 4 times 3, it's 12, and it's 2 modulo 5.
Sorry, I think it's easier to count in binary, because in binary we have addition, not multiplication.
Yes, maybe.
Okay.
Write it in binary and tell us the answer in our group, in our multiplicative notation.
Okay, we multiply 2 on 3. Am I right?
It depends on the isomorphism.
No. I mean, in this case, we need to multiply 2 on 4.
We need to multiply 2 by 4 to the minus first power.
And yeah, and it is 4 in the minus first power is 4 in third power.
And what is 4 cubed?
4 squared is 1 0. Then 4 cubed is 0 1, and it is 2.
4 cubed is not 2, because 4 cubed by 4 should be 1, and this is 3. So please check that the multiplication you use in binary corresponds to the multiplication of the elements in our group.
But in binary, it is not multiplication, it's addition.
I'm afraid I don't get your correspondence between numbers in our group and binary.
Well, okay, yeah, I think I'm only confusing, sorry.
Not a problem. So let's find 4 cubes. Let's find it directly. Let's take 4 and multiply by 4 and multiply by 4. 4 squared. 4 squared. What is 4 squared? It's 16, which is 1, yeah? And 1 by 4 equals 4. But knowing that 4 squared is 16, which is 1, we can notice that the inverse for 4 is also 4, yeah? So we don't even need to find the third power, actually. So we have to multiply this 2 to 4 to the minus first power, which is also 4, yeah? And this equal to 8, which is 3 modulo 5, yeah? So the first number of our secret message is 3. Is it clear?
Quite complicated.
Quite complicated. So everything you need to know now, you need to know the rule, how the message was constructed. So the second person wants to send us, actually, the person wants to send us this number H. This is the information the second person needs to send to us, yeah, H. But how to...
Excuse me.
Mhm.
Can you please use another color pen? Because it makes really messy, and I don't quite get what's going on here.
Okay. I'll take green. I'll take green. Okay. So the second person wants to send us this number H, yeah? And both of us know this number K. You know already. K is G to the power AB. So only me and the next person know this number K. And what is the message? It's not private. The second person takes these two numbers, the actual message H and our key K, multiplies these numbers and send this number M. So we get this number M, but our goal is to find this number H. How to find it? Knowing M and K, it's not very complicated. We need to multiply M by the inverse number for K. Yeah? This equality. Is this clear?
Yes, it's clear.
Okay, so let's find it directly. We know the message 2, so we need to multiply 2 by the key, which is K, which is 4, to the minus first power. Minus first power in our group. Do you remember that our group was a multiplicative group of reminders modulo 5? So we take 4. What is the inverse for?
I have a question. And isn't it simpler to just find an inverse for 4?
We found the inverse for 4. Then 4 to the third power. Yes.
Yeah. Yes. I mean, in this exact...
You may merely guess it. You may merely guess it. But how would you guess it in a very huge group? So here is the rule. Take K and raise it to the power n minus 1. So this is a common rule and it always works. But now in our case, actually it's very easy to guess the inverse number, which is also 4. And we find it some way. Okay, and then we merely multiply 2 and the inverse for 4, which is also 4, and we get 3 modulo 5, yeah? And this was the message H, the secret message the second person wanted to send to us privately. Is it clear? Is it more clear now?
Well, yes.
Mm-hmm. So look here. The next one is 3. How can we find H now? H is M, which is 3, to the 4 to the minus first power, which is also known as 4. 3 by 4, it's 12, and it's 2 modulo 5. So the next part of the message is 2. The third one is the same as the first. So let me circle these ones. And the fourth one is 4. So h fourth equals to 4 by 4, which is 1. No? Oh, no. I'm sorry. The
Our third, like our third is third element is 2, but we already counted.
The third element is 2, and it's the same that the first, and the first was 3. The first secret message was 3, so the third secret message is also 3. Yeah, you're right. And the fourth message is 1. We multiply it by 4, and it's also 4, and the fourth secret message is 4. So the sequence is the following: 3, 2, 3, 4. You see? And we can also decode using our binary notation. It's 1, 0, 0, 1, 1, 0, 1, 1. So that was the original message. Okay?
I have a question. And why are these binaries given? Because actually we don't need them.
Actually, we don't need them for our coding encoding procedure. But
yes,
in real life, not during algebra classes, in real life you have some alphabet. Look at the problem number 4 of your homework. And in real life, you always don't need to send some arbitrary numbers, or not very arbitrary numbers. You need to send some actual text, some actual information. Consists of letters of some alphabet, for example, Latin alphabet. And you need some rule to decode these numbers to natural numbers.
Yeah. I got the point that we need to encode our letters, or like some same data, and we used ASCII on our C++ course. But I mean, I got what encoding means. But my question is, why do we put it in these tasks? Because actually we do not need to transcode from the from our like initial sequence to.
Okay, I get it. It's a toy example that shows you that even if we don't speak much time about this procedure, it can be done, and it's not very difficult. The most difficult part is mathematical part, algebraical part of all these questions. So, but we can easily apply it to real problem of sending binary sequences. Just to give you a kind of example.
Okay, got it. Thank you.
So let's find something else. Let's look at the problem number 6. Okay. Here we have Z17 start. Yeah, we already worked with this group 2, and here G is chosen as 3, the base of all of our powers. And we have some set F4, which is a set of strings A0, A1, etc., where all the numbers is are zeros or ones. So the first task is to show that the map from F4 to Z17, described as in the problem by the rule 1 plus A0 plus 2A1 plus 4A2 plus 8A3, is a bijection. So let's show that this is a bijection.
And this is pretty simple because
Explain, please.
it is pretty simple because we just go from one base to like from 10 base to 2 base.
So it's a binary binary notation for our number.
Yes, I mean it's actually our number just in base 2 в системе исчисления с основанием 2. Sorry.
Binary, in binary. So this string is a binary string, and this sum is a decimal representation. If we compute the sum, we'll receive the decimal number. Yeah.
I have another question.
A3, A2, actually, this one is a binary. And it's merely binary. It's merely our number plus 1. And this one doesn't mean anything for our bijection. It means that all the numbers are not from 0 to 15, but from 1 to 16. You see?
Yeah.
So for every set of eighth, these numbers are from 1 to 16. And they are merely a decimal representation of some binary numbers, of what binary numbers, of all binary numbers from 0 to 15. And we move them by 1, so they are from 1 to 16.
And I have a question. In our group that starts 17, our operation is multiplication, and
Right.
when we consider our group F4, do we mean that our operation remains same, or we change operation? Because
actually F4 is not a group, it's merely a set, and the map is a bijection but not an isomorphism.
Oh, okay, got it.
It's only a map of sets, so we don't think about the operations and about the preserving of the operation, because there are no any operation yet in F4. So it's a bijection. Yeah, it is clear. It maps strings from F4 to natural numbers from 1 to 16, actually. Yeah, and for every number from 1 to 16, we can find those string which was mapped to this number. So this is this mapping is surjective, and it's also injective. And is it clear? Is it clear that this is a bijection? Or
Yes.
Okay, so let's solve the second part of this problem. B. Let A be 5 and B be 3. We need to complete public keys R and S, as usual. Let's compute them, but in our new group. So, what is G? G is 3. So, R is G to the 8th power, which is 3 to the 5th power, and S is G to the bth power, which is 3 to the 3rd power.
They have to be congruent 17, yes?
Modulo 17. Everything is modulo 17. Tell me, please, what are the answers?
For 3, it is 9. Oh, no, it's not 9. Sorry.
Mhm.
It's 10.
It's 10. Right, you are. Because it's 27, 27 is 10 modulo 17. And for 3 to the 5th power, we already know that to the 3rd power it's 10. And then we need to multiply it by 3 2 times and find the reminders.
It will be 100 remainder after, like, it's congruent to 100 modulo 17.
And isn't it easier to find 10 by 3, which is 30, and it's 6
Oh, yeah.
modulo 17, and then
36 modulo
30.
17.
30 modulo 17, is it 6 modulo 17? No, it's not. It's not 6 modulo 17, it's, what is it? It's minus 6. Maybe it's 11 modulo
Wait,
17.
it is 3 multiplied by, it is 90 modulo 17.
It is 30, actually. No, or 90 modulo 17, speaking about the 5th power. So what is this one? This 13 modulo 17, I suppose. And then we need multiply 13 by 3, which is 39. And this is actually 5 modulo 17. Is it clear?
Yes.
Okay, so the second point done. The next one, we need to compute r to the power of b and s to the power of a and check that the results are the same. Let's check. Or maybe let's, it's a bit boring, but we need to encrypt the sequence. So how do you find r to the power b and s to the power a? Could you tell me the answer?
But actually, we don't need to compute it. We just know that we can raise to the power, like, raise g to the power of b, raise to the power of a. It will be g to the power b multiplied on a. And the same thing we can do for our public key.
Do please and tell me the answer.
Okay.
Please, on your own, find the answers. And we'll check it in a minute.
By saying "do please," do you mean to do it on the paper, on the board, or what do you mean?
On your own. If you want to do it on the board, you may do it on the board. But I suppose that all of you can do it on your own, and we can compare our answers. And check whether the answers are the same.
And how can I share it?
Use the chat, please. But speaking about the answer, you may tell us merely the answer, and that's all. not of the computations, but only the answer. So let me help you. Knowing that we already found what? Found R, which is 5. Let's take 5 and raise it to the third power. To the second power, it's 25, and it's 8 modulo 17. And I need to multiply it by 5, and it's 40 equals 6 modulo 17, because 34 is 17 times 2. So the answer is 6. You can check that s to the 8th power is also 6, and g to the power ab is also 6. Okay? I hope you'll train this working on your homework. So let's look what's next. Now we need to take some sequence and cut it into some pieces and decode it. So let's discuss the plan. So we have some sequence, and we need to cut it into 2 pieces, S1 as S2. So 1, 1, 0, 1 is a sequence of our A0, A1, A2, A3. Yeah. Then we need to map each piece. So speaking only about the first one, we need to map the first piece and into H1. How do we map it? Using the rule. So we take 1 plus A0, which is 1, plus 2A1, which is 2, plus 4A2, which is 0, and plus 8A3, which is H. So this is 12 from our multiplicative group. And this is the message. We now need to encrypt it. How do we do the encryption? We need to multiply. So the message is H multiplied by our key K, as in the first in the previous problem. Do you remember? Yeah. So knowing that H is 12 and knowing that key is 6, we get 12 by 6, which is 72, which is something modulo 17. Okay? So is it clear how to solve this problem? If it's not clear, please ask questions, and we'll end our class.
It is not clear.
It's not clear. Let's look.
Okay, we take our S and decode it to our to element of our group. Am I getting it right? Correct.
Yes, actually. So this is about your previous question, one of your previous questions about why do we have a table in the problem number 5? The correspondence of binaries and the elements of our group. So in this problem, we don't even know the numbers of our group to decode and to send them. We need to construct the numbers, to find the numbers, knowing the original message. So we know the rule. We take the first 4 digits from the original message, find the element in our group, knowing these 4 elements, binary elements, and then we act as usual, using our procedure of coding and decoding.
Okay, my question is where our H. Okay, we have one S, and then we split it on two different secret keys.
Mm-hmm. On two
and
different
then-
messages.
And then for each, okay, and then for each two elements from our group, we have to count the message, to
Yeah.
encrypt message.
Yeah, we found two messages, M1, which is H1 by K, and M2, which is almost the same. And then we send them, and then we can decode. Knowing M and K, we can decode, and we can find original binary sequence.
Mm-hmm.
Oh.
Okay, I think it's. And how can we obtain the original sequence?
How can we obtain the original sequence? So when we end our decoding procedure, we get a number, actually two numbers, which are the elements of our multiplicative group. And we know that there is a bijection from F4 to our multiplicative group, but that means that there is an inverse bijection, which maps our numbers from the multiplicative group to binary sequence from F4. And using this inverse bijection, we find all the numbers.
No. Okay. I got the point where I misunderstand, but I thought that S is our key, is our public key, is our. Yeah, it's our.
It's a notation here. Some letters were missed. Never mind.
Okay.
So-
Am I getting right that S1 and S2?
Mhm.
S1 and S2 is not our keys. It is just message which we
Yeah,
want.
that's our
Which we
original.
want to.
So
to
the S in the C point and S in the D point are not the same.
Oh, okay, got it. So in S1 and S2, two strings which we want to encrypt, and then we want them to decrypt, decrypt them back. Okay, got it.
All right. Okay. Do you have any other questions? Because we ran out of time now, and we have to end our class.
I have one question, about organization. Just I've tried to connect the consultation which has been on Monday, but
It's in the link from Wiki.
yes.
And what went wrong?
I couldn't connect because it said to me that the host.
Okay, you may
Cancel.
write me in the Telegram if I'm not online. Do you remember my Telegram? I'll write it down.
No, actually, I don't know it.
Okay, let me type in. If you want to connect to our Zoom Q&A, and if you see that I'm offline, please send me a message via Telegram, and I'll connect. Okay.
Okay, got it. Thank you. Can I just message you to save you in my? I will message you to save.
Really. Mm-hmm.
Okay, thank you.
So let's end our class now. If you need to move our Q&A from the Monday, which is holiday, please let me know. But we'll have Q&A on Monday. If you need to move it to some other day, please send me a message or a letter to my to both of my emails, work and home email. So see you next Thursday or on the Q&A, and good luck with your homework. If you have some questions, please feel free to send me messages via Telegram or my email. Goodbye and good luck. Thank you for today's class.
Thank you. Bye-bye.
Thank you. Bye.